DFG Science TV, the start of nature, life in an open pit mine, from a lunar landscape to an ecosystem.
Normal soil below a Brandenburg forest. The properties of this soil are, however, the result of many thousands of years of development and a series of complex processes. Upon closer examination of the subsoil, one can see various layers. Soil scientists call these horizons. The top layer, the A horizon, contains humus. The grey layer below it is formed by acids from the humus. These leach minerals out of the sand. What remains is a grey horizon. Down even further, materials from the topsoil have collected. These give the layer its distinctive brown colour. A clear sign, primarily iron compounds are deposited here. This soil is called podsol. It's typical of sandy areas. For comparison, here's a look at a very young soil. We're at the Welzow South open pit mine, not far from Chicken Creek. Even upon closer inspection, no horizons can be seen. It will take many years before humus is deposited here in the upper layer. The top dark horizon of the soil will form. With young raw soils, this layer is normally non-existent. At TU Cottbus, scientists want to learn more about the processes that are important in the formation of soil. To that end, they've constructed a microcosm system in the laboratory. In principle, a microcosm system is a system in which a number of plexiglass cylinders are arranged, like you see here in the background. And these columns, or cylinders, are filled with soil, allowing the various processes that take place in the soil to be studied. As with an incubator for small babies, the scientists monitor the conditions of the young soil. Temperature and precipitation are precisely dosed, and the seepage water collected. Precipitation, of course, also determines the hydrologic balance and affects chemical solution processes, in the soil, for example. We have lime in our Chicken Creek substrate, and with time, that will be dissolved by the precipitation. And anions and cations will continue to be dissolved from the minerals or from the substrate, and with time these will be moved further down in the soil. And here we can examine which ions these are and in what quantities they're present. The scientists are also observing the development of the young soil directly on site. In soil shafts, they draw out the soil water for analysis later in the laboratory. Admittedly, that's easier to do in the laboratory, but unlike in the laboratory, the researchers cannot program the soil moisture here. They instead employ various measurement techniques, from the measurement probe to ETH Zurich's radiometer. With the radiometer, the researchers observe the soil moisture on the surface, a technique which, incidentally, will also be used later in a satellite. This will measure soil moisture across Europe. The water transports the nutrients in the soil. Many nutrients find their way into the soil through the decomposition of organic materials, like dead plants. But what path do they take in the soil? We can track that by sampling the actual microorganisms and then observing what portion of carbon from the organic layer finds its way into the microorganisms and what portion seeps through the soil. Plant remains marked with carbon isotopes play a key role here. What do the humus and carbon tell us about the development of the ecosystem? Find out next time.
Visit DFG Science TV for more information. Awaken the researcher within you.